In our previous lecture, we started talking about formulating linear time invariant resistive circuits in order to be able to solve them. And the first approach we talked about last time was called the node voltage analysis, and the idea was very simple. It was that you formulate the circuit in terms of node voltages, by which we mean you write at each node equations imposed on the circuit by KCL in terms of node voltages. Okay, and if you had only independent current sources, or current sources in general in your circuit, then the method flowed smoothly. But when you had certain voltage sources in the circuit, then sometimes it may be not easy or possible to write the currents through them in terms of node voltages. Okay, so in such cases, we have to modify slightly our method. Okay, so here was the last example that we talked about, where we have two voltage sources. This voltage source is not really problematic because it's between this node and the ground node. Therefore, we direct the voltage, this node voltage, okay, it equals Vs1. Since it's an unknown, this voltage source doesn't cause any problems. Okay, whereas this voltage source, if we try to write KCL either at this node or that node, will present a slight problem. And the problem is the following: you can write the current in terms of node voltages, this current. Okay, you can write this current in terms of node voltages, but when you try to express this current, okay, you cannot use Ohm's law because this is not a resistor. Therefore, it's not apparent what to do, okay, with that current. So what we do, or our suggestion was, and we talked about the suggestion under the title method 1, was increase the number of your formulation variables. Here, the number of our formulation variables are E1, E2, E3, and that method suggests that consider this current, which you cannot express in terms of your node voltages, also as one of your formulation variables. Okay, so when we try to express this current, we don't do anything but just write I, or this current, we just write minus I. Okay, so we write KCL here, and KCL over there, so that makes 3 equations, but we have 3 unknowns, E1, E2, and E3. Excuse me, we have 4 unknowns, E1, E2, E3, and I. Therefore, we require one further equation, and that equation came from KPL, not KCL, through the following constraint. We wrote that E1 minus E2 equals Vs2. That was our 4th equation. Today, we will improve that method and get rid of that I altogether and see how we can formulate the circuit with 3 formulation variables, E1, E2, and E3. Okay, and then we will move on to the dual method, namely the mesh current analysis method, in which we will formulate the circuit in terms of mesh currents. Okay, but now let's talk about the modification of method 1. Last slide. So method 2. Write KCL, pretending that the 2 nodes between which there is voltage source are a single node. Okay, such node is called a supernode. Okay, it's called supernode. Now this suggestion says us the following. Forget about this current now. Okay. And here are two nodes between which there is a voltage source, and we cannot express the current through that voltage source, okay, directly in terms of the node voltages. So what this method suggests us is the following. Combine these two nodes in the sense that consider a closed surface that encapsulates both of them, okay? Now remember that to be able to write KCL equations, we don't really need a node, all we need is a closed surface. So the closed surface that's being suggested by that method is this, okay? And now, instead of trying to write KCL individually at this node and that node, just write a single equation in this new closed surface, which we call a supernode. So this is supernode. Okay, so let's go ahead and do that. So this is the previous example. We're now revisiting it. Okay, under our new method. So supernode, let's call it node S. Let's write KCL at this node. Writing KCL for supernode simply means that we're going to sum all the currents leaving that. So we have this current, this current, this current, that current. By KCL, the sum of those four currents must equal to 0. This current is E1 minus this node voltage, which is Vs1 over resistance between R1. This current is E1 over R2, because R2 is directly between second node and ground node. And we have this current plus E2 over R3, and so on. Finally, E2 minus E3 over R4. And by KCL, this sum must equal to 0. Okay. And then we have the other node, node 3. Let's write KCL also there. So we have this time this current, which is E3 minus E2 over R4. This current, which is minus IS1. And finally, this current, which is E3 over R5. And that sum must equal 0. Okay. Now, formulation variables are E1, E2, and E3. So that means we have 3 unknowns. But KCL gave us only 2 equations. We need one last equation in order to be able to solve for the known voltages. And that last equation is called the constraint equation, and coming from KVL instead of KCL. Okay. Now the constraint equation is, here we have ES2, which makes sure that the voltage difference between E1 and E2 equals Vs2. Okay. And now we have 3 equations, 3 unknowns, and we're ready to solve this equation. So let's put those equations in matrix form. Okay. So these are node equations. And let's write down node equations in matrix form. Okay, so these will be called node equations in matrix form. Okay, where this vector contains our formulation variables or the unknowns. In this case, we have 3, E1, E2, E3. This is a 3 by 3 matrix whose entries are coming from the circuit parameters, or in particular coming from those 3 equations we wrote down. And here we collect the knowns. Okay. Okay, so let's fill in the entries of this matrix. For the first row, we'll look at the first equation, the supernode equation. For E1, we have 1 over R1 and 1 over R2. 1 over R1 plus 1 over R2. For E2 we have 1 over R3 and 1 over R4. 1 over R3 plus 1 over R4. And finally, for E3 we have minus 1 over R4. Minus 1 over R4. And what remains, we throw to the other side, and what remains is minus Vs1 over R1. Okay, on the other side it becomes plus Vs1 over R1. So that's the first row. For the second row, we look at the second equation. For E1 we have nothing. For E2 we have minus 1 over R4. For E3 we have 1 over R4 plus 1 over R5, and what remains is minus IS1. We throw it to the other side, it becomes plus IS1. And finally, for the last row, we look at the last equation, which is not a K-sub equation, but a KVL equation, which says E1 minus E2 equals Vs2. E1 minus E2, and nothing for E3, equals Vs2. Okay? And this is the equation in the matrix form. Okay, now let's see another example, this time with dependent source. So far we haven't yet seen any example with a dependent source, so that would be a nice beginning. This time, let's obtain some numbers from the circuit. So this is our circuit. Okay, with an independent source and independent source. The rest are LTI resistors. 4 ohm, 3 ohm, minus plus Vx. This is the control voltage for the dependent source, Vx. And here we have a constant current source, pumping current at 5 amps. Okay. And this is 2 ohm. And the question is, find the power absorbed by the 3 ohm resistor. Okay? We're interested in figuring out the power consumed by this resistor. Okay. So all we have to do is therefore figure out this voltage, and power is voltage squared over resistance, or this current, then it's resistance times the current squared. Okay. Now let's apply node voltage analysis method for this circuit. So we have to choose first. The very first step is labeling. So first we have to choose a ground node, and then we label the remaining node voltages. Let this be our ground node or reference node. Okay. And the other nodes that remain are, here we have one, here there's another one, and this is the third node. Okay. Note that here, this is not an extra node, this node and that node, they're the same thing because they're just connected by wire. Okay, so they have the same voltage. Okay, so it will be no problem. Try it. Okay, so this is E1, this is E2, and this is node 3, and the corresponding voltage is E3. Okay, there will be no problem writing KCL at the first node, but if you try to write KCL in terms of node voltages, either at node 3 or node 2, there will be a slight problem. The problem has to do with the fact that we cannot express directly in terms of node voltages is current that's passing through that dependent source. So what we do then is we follow the suggestion given us in method 2, it's here, and consider node 2 and node 3 as a single closed surface, a single node. In other words, let's treat this as our supernode. Okay. This is our supernode. So what we're going to do is we're going to write KCL here, no problem. We're going to write KCL at the supernode, again, without any problems. And finally, we require one further equation because we have 3 unknowns. And that further equation, or the last equation, will be coming from the constraint imposed on the voltages, node voltages, by this dependent source. Okay, it's quite straightforward. And then, once we have the equations, we may try to figure out E2, and then once we have E2 is this voltage plus minus E2 squared over 3 will give us what we ask, the power of the 3 ohm resistor. So KCL at node 1. Okay. So here we're writing KCL at node 1. So that means we're going to add this current, and this current. That sum must equal to 0. Note that this current equals this current plus that current. Okay. So basically we're summing this current, this current, this current, and that current. We're going to have 4 terms, and that sum of 4 terms equal to 0. So this current is minus 5. Okay, and then we have this one, which is E1 minus E3 divided by the resistance in between, E1 minus E3 over 2. And then we have this current, which is E1 over 4. And finally, this current is E1 minus E2 divided by 2, and KCL says that the sum must equal 0. Okay, so let's call this equation 1. Then we have KCL at the supernode. Okay. This time we're going to add 3 currents: this current, and that current. And the sum equals to 0. This current is E3 minus E1 divided by the resistance in between. And then we have this, which is E2 minus E1 divided by 2. And finally, this current is E2 over 3. And that's our second equation, KCL. And that's all we can get from KCL. Okay. Whatever remains, we have to use KVL. And that's, for that, we'll look at the constraint imposed on the known voltages by that dependent source. Okay. So, constraint equation. E2 minus E3. E2 minus E3, because the polarity of this dependent source is plus minus, like that. E2 minus E3 equals Vx. Okay. Note that we cannot leave this equation as it is, because that's a dependent source, meaning that we don't know what Vx is at this stage, at least. Okay, this is also an unknown. But in our equations, the only unknowns that we allow are our formulation variables, namely E1, E2, and E3. Therefore, somehow we have to express Vx in terms of our node voltages. So Vx is here, this voltage, it's given, and this voltage is simply E1. Okay. Therefore, we know what Vx is, or we can express Vx in terms of node voltages, E1. So we substitute this Vx by E1. So what we have here is E2 minus E3 equals E1. That's our third equation. Okay. Now we have three equations, and all in terms of our formulation variables. Therefore, we're ready now to find the answer. Okay, let's do the elimination method, starting from equation 1. We have something times E1 plus something times E2 plus something times E3 equals 5. Okay. So for E1 we have 1/2, 1/4, and another 1/2. Okay. And then for E2 we have minus 1/2, and for E3 we have minus 1/2 equals 5. Okay. Then using third equation, we can replace this E1 by E2 minus E3. And if you do that, this is what we have: 5/4, it's this sum, times E2 minus E3, because that's what E1 is, minus 1/2 E2 minus E3, 1/2 E3 equals 5. And if you reorganize the terms, this gives you 3/4 E2 minus 7/4 E3 equals 5. Okay, this is our equation number 4. Let's move on to the remaining equation. Okay. We look at now the second equation, which we were given by the Supernode, right in case of Supernode 2. Again, we have minus 1/2 plus another 1/2 E1. Okay. For E2 we have 1/2 plus 1/3. Okay. And for E3 we have 1/2 plus 1/2 E3 equals 0. Okay. And then using, again, equation 3, we can replace that E1 by E2 minus E3, and that will give us this makes 1, so we have minus 1, then we have E2 minus E3 plus 5/6 E2 plus 1/2 E3 equals 0. And if you reorganize the terms, you have E3 equals 1/9 E2. That's our equation 5. Okay. And now if you plug E3 equals 1/9 E2 into this equation, equation number 4, then we have E2. And E2 is the voltage of the 3 ohm resistor. And therefore that voltage squared divided by the resistance will give us the power of the 3 ohm resistor. So let's do that. 4 and 5 implies 3/4 E2 minus 7/4 E3, and E3 is 1/9 E2 equals 5. Now this is an equation only in terms of E2, and which gives us E2 to equal 9 volts. Okay. And once you have E2, you can figure out E3 and also then E1 easily. Okay, so we know that E2 is 9 volts. Then power of 3 ohm resistor equals the voltage of that resistor squared divided by the resistance, and the voltage of that resistor is no other than the second known voltage E2. Okay. So we have E2 squared over 3, and we have figured out E2 equals 9 volts, so we're talking about 9 squared over 3. That makes 27. 27 watt That's 1 watts. Okay. So never forget the units. Okay? Otherwise, the answer doesn't make much sense. Okay, let's move on to mesh analysis method. But I suggest for those of you who have time, as an exercise, to redo the example, this time choosing a different ground node. Okay, redo the previous example. By choosing node 3, node to which we assign E3 in the previous labeling as ground. Okay, so that's more or less all there is to it about node voltage analysis method. Now we're going to talk about the dual method, where we will try to formulate. We'll see how we can formulate a circuit in terms of mesh currents. Okay. Now, which method is better? Well, it depends on the situation. Sometimes it may not, both may be equivalent in the sense that both take the same amount of time to formulate and solve, but sometimes the topology of the circuit is such that it's better or faster to formulate and solve it in terms of node voltages, or sometimes the reverse in terms of mesh current. So it's up to you. So you have to look at the circuit and decide for that particular situation. But it's always good to have as many methods as possible in our pockets. Okay. Now, mesh current analysis. Okay. It's the dual of node voltage analysis. Now, the idea in node voltage analysis method was formulating a circuit in terms of node voltages using KCL. Now here the idea is formulate a circuit in terms of mesh currents using KVM. So the idea is to solve for mesh currents by writing voltage equations imposed on the circuit by KVL. Writing KVL at inner meshes. Okay. So let's apply this very simple idea directly on an example. Consider the following LTI resistive circuit. R1, R2, R3, R4. This is VS1, and this is VS2. Okay. Now, with non-voltage analysis method, we were happy with current sources. Now we're happy with voltage sources, because we write equations. We write voltage equations, and whenever you have a voltage source, you directly know what the voltage is. Okay, so these are good guys for mesh current analysis. Now, with non-voltage analysis, we said the very first thing that we should do is labeling, and it's true also for mesh current analysis. The first thing you should do is you should label the mesh currents, okay, your unknowns. So we have 1, 2, and 3 meshes here, so that means we have 3 mesh cards. And let's label them as follows. This is I1, okay. This is I2, and this is the mesh card for the 3rd mesh. By convention, their directions are all chosen to be clockwise. Okay. So formulation variables are I1, I2, and I3, 3 mesh cards. Okay. These are mesh cards, and by convention, their directions are chosen clockwise. Okay. Now, once we have the proper labeling, now what we will do is we'll write KVL at each mesh. And writing KVL at each mesh means that here is a mesh, and to this mesh there are 3 components associated, R1, R2, and this voltage source. And what we will do is, as we go along the direction of the mesh, we will sum up all the corresponding voltages, plus minus VR1, plus minus VR2, and finally plus minus this voltage, which is minus VS1. Okay. And that sum, because it's a closed path, that's a loop, by KVL must equal to 0. And that's how we obtain the equations. KVL at mesh 1. Okay. Suppose that we start from this point, and this is the direction of our mesh clockwise. So what we will do is we will sum these 3 voltages, plus minus, and plus minus. Okay, according to the direction of the mesh. First voltage here is plus minus this voltage, and since the polarity of this voltage source is minus plus, what we do is we put a minus VS1 in, okay, minus VS. Okay, so that's our first voltage, minus VS1, and then we have plus minus this voltage, plus minus, which is VR1, plus VR1, and finally we have plus minus this voltage, let's call it VR2, plus VR2. Okay, by KVL that equals 0. Now there's a problem with that equation. The problem is not that it's incorrect, it's correct. Okay, those 3 voltages sum to 0. But the problem is that we want our equations to be in terms of our formulation variables, okay, namely the mesh current. But here, okay, there's no problem with this term, it's known, it's the voltage of an independent voltage source, but the remaining 2 voltages, the voltages of the resistors 1 and 2, they are unknowns, and they are not in terms of mesh current. So we have to express them in terms of mesh current. But that's very easy, because VR1 is IR1 times R1, okay. R1 times IR1, and what's IR1? IR1 is, okay, according to our labeling, it's this current, and this current is, okay, this branch is between first mesh and 3rd mesh, and the direction of the current that we're talking about is from left to right, and it's in the same direction with mesh number 1, it's in the opposite direction with mesh number 3, therefore this current is I1 minus I2. Okay. So R1 times I1 minus I2. Likewise, the R2 is R2 IR2. Okay. And this is plus minus VR2 by passive cycle dimension, this is IR2. Therefore we're talking about this current. So it's in the same direction with the first mesh, in opposite to second mesh. Therefore, this current is I1 minus I2. R2 times I1 minus I2. Okay. Therefore, we can rewrite that equation in terms of our formulation variables, and that gives us, we guess 1 plus R1 I1 minus I3 plus R2 times I1 minus I2 equals 0. And now we're happy with this equation because it's only in terms of our formulation variables. Okay. So let's call this equation number 1. Let's quickly write down the remaining two equations by writing KVL at mesh number 2 and mesh number 3. Okay. Okay. KVL at mesh number 2. Now we're here. Suppose that we start from this point, okay? The direction is clockwise by convention. So the first voltage is this, plus minus. Since it's in the opposite direction with the polarity of Vs2, so the first thing that we write is minus Vs2. Okay, and then the next component is this. This time, the polarity is such that plus here and minus here, because the direction is clockwise for the second mesh. Plus minus. Here that voltage is R2 times this current, from bottom to top. And this current is, since it's in the same direction with the second mesh current and opposite with the first mesh current, this current simply is I2 minus I1. Okay. Therefore, R2 times I2 minus I1. And finally, this is the third and last component in this mesh. And the voltage plus minus is R3 times this current. This current is in the same direction with I2 and opposite to I3. Therefore, this voltage is R3 times I2 minus I3. Okay. So that's our second equation, and everything is in terms of mesh currents. And finally, KVL at mesh number 3, our last mesh. Suppose that we start from this point, plus minus this voltage is R4 times this current, and this current is. So this branch only touches one of the meshes, it's mesh number 3. And this current is the same as, the direction of that current is the same as the direction of I3, therefore this current is I3. Okay? And this voltage plus minus must equal, therefore, R4 times I3. Okay, then next up is this voltage, plus here, minus here. Therefore, it's R3 times this current. This current is in the same direction with I3, opposite to I2. So we have R3 times I3 minus I2. And finally, for the last guy, we have R1 times I3 minus I1. And this is our last equation. So those are the mesh current equations as we did with node voltages. Let's put them in a more compact form, that is in matrix form, and we will move on to other examples. Okay, 1, 2, and 3. Okay, give us this matrix equation. Here, this vector is the vector that contains our unknowns or formulation variables, I1, I2, and I3. It's called or labeled IM in general, mesh current vector. Okay. Then here we have the vector that contains the knowns, and here we have a 3 by 3 matrix that, whose entries are coming from the circuit parameters, or in particular from those equations. Okay, let's figure out the entries of this matrix. For the first row, we look at the first equation. First equation is here. For I1, we have R1 plus R2. For I2, we have minus R2. For I3, we have minus R1. And whatever remains, we throw to the other side. So here we have the S1. Okay. For the second row, we look at the second equation. For I1, we have minus R2. For I2, we have R2 plus R3. And for I3, we have minus R3. Okay, and what remains, we throw to the other side, it's the S2. And finally, third equation, third row. For I1, we have minus R1. For I2, we have minus R3. And for I3, we have R1 plus R3 plus R4. And nothing remains, that means that entry is 0. And this matrix that forms is denoted usually by a capital Z, Zm, and it's mesh impedance matrix. Okay. So this is mesh equations in matrix form. Now, in this example, all the sources were voltage sources. And whenever we have voltage sources, we don't have any direct problems writing KVL equations. But whenever we have current sources in our circuit, sometimes it may be difficult to express, or impossible to express voltages through them directly in terms of the formulation variables, mesh currents. Therefore, we have to modify the method a little bit. Okay. So we're going to talk about that now. Mesh analysis with or under current sources. Consider the following circuit. S plus minus Vs R1, R2, R3, and R4. Okay. So we have 3 meshes. Let's label them. This is, let's say, I1. This is, let's say, I2, and this third one, let's call it I3. Okay. Now, if you try to express the voltage of this current source in terms of mesh currents, it will not be possible, okay, directly possible. But then again, since this current source is between an inner mesh and outer mesh, okay, it's not between 2 inner meshes, it directly gives us the knowledge about one of the mesh currents, okay? So in fact, this is I3 and this IS is in the same direction, and therefore I3 directly equals IS. So I3 therefore is not one of our unknowns, hence we don't have to label that as one of our formulation variables. In fact, we have only 2 unknowns, I2, I1 and I2. And since this is not a formulation variable. We don't have to write KVL in this mesh. All we have to do is write KVL here, write KVL there, and that we can do easily. Okay. So note that. I3, the third mesh current, equals IS. And IS is the current of independent current source. That means it's known. Okay, therefore I3 is not an unknown. Therefore, known. Okay, that leaves us with two formulation variables or two unknowns. I1 and I2. So let's quickly write KVL at mesh 1 and mesh 2, put them in matrix form, and then we will move on to a little bit more complicated example. So KVL at mesh 1. Okay, that's right. This, suppose that we start from this point, so what we're going to do is we're going to add up 3 voltages, plus minus this voltage, plus minus that voltage, and finally plus minus this voltage. Okay, plus minus this voltages are 2 times this current, and this current is I1, okay, minus I3. And I3 is IS, therefore this current is R2 times I1 minus IS. R2 times I1 minus IS. And then we have this voltage here, plus minus. It's R3 times this current. This current is in the same direction with I1 opposite to I2. Therefore that voltage is R3 times I1 minus I2. And finally, we have this voltage, which is directly known as Vs. Okay. Plus Vs by KVL, that equals 0. And let's do the same thing at the other mesh. Okay, suppose we start from this point. Plus minus that voltage is R1 times this current. This current is I2 minus I3. I3 is IS. Therefore, it's I2 minus IS. Then we have this voltage, R4 times that current. R4 times I2 directly, and finally we have R3 times this current, and it's I2 minus I2. I2 minus I2. Okay, and those 3 voltages must equal to 0. So that's the mesh equations for that simple example. Let's put them in matrix form. We have only 2 unknowns, 2 formulation variables, therefore mesh impedance matrix will be 2 by 2. Here we have I1, here we have I2, and here the right hand side is where we keep the knowns, and here we have the circuit parameters, that's the entries. For the first row, let's look at the first equation. For I1 we have R2 plus R3. For I2 we have minus R3, and what remains is R2 IS and minus Vs. For the second row, we look at the second equation. For I1 we have minus R3. For I2 we have R1, R4 and R3. And what remains is R1 times IS. And this is the equation in matrix form. Now, next lecture, we will see how to deal with circuits when we have a current source between 2 inner meshes.